Logarithm is basically the opposite of exponentials. Let's take a couple examples in base 2. We could be asking 2 to the third is equal to what? We could also be asking 2 to the 1/2 is equal to what? Or maybe in a different base, let's say base 5. 5 to negative 1 is equal to what? Well, the answer here is 8. 2 to a third means 2 times 2 times 2. The answer is 8. Second question, 2 to the 1/2. Base 2 to the power 1/2. And power 1/2 means the square root. 2 to the 1/2 is square root of 2. You can also write this in decimal as 1.4142, etc. Next, 5 to the negative 1. What is the negative power? Negative power means 1 over. 5 to the negative 1 is 1 over 5. You can also write this as a decimal, 0.2. These are questions that are asked in exponential form. The opposite of exponential would be, I'd be giving you the number 8, and I ask you in base 2, 2 to the power what is equal to 8. So instead of giving you the 3 and asking 2 to the third equals to what, I give you the 8 and I ask 2 to the what is equal to 8. Same with the other two questions. And so the answer would be that question mark is equal to, going to be equal to some function of 8, where that function could be written the opposite of base 2 exponential. And the answer is 3 because you know 2 to a third is equal to 8. So the answer here is 3. Let me put the 8 in red to make it consistent. Well, the shorthand for all of this verbiage is logarithm. It's logarithm of 8. But we also need to specify that we're working in base 2. So I'm going to put the number 2 in the subscript here. And that is equal to 3. I'm going to apply this to the second question. The second example asks a question about the radical 2. So I want to be able to go from radical 2 backward to the answer of 1/2. I want to be able to make it equal to 1/2 like this. And the function in front, again, is the opposite of base 2 exponential. And instead of saying it long like that, I go log base 2 of radical 2. Third example, I want to go backward from 1/5 backward to the number -1. Then I use log base 5. If you compare all of these expressions, in the first example, the 3 used to go with the base 2 in the exponential, and the 8 used to be the answer. Once I've written in logarithm form, the 8 goes with the base 2 in logarithm, and 3 is the answer. Second example, the 1/2 used to go with the base 2 in exponential. By the time I rewrite as logarithm, it's the square root of 2 that goes to the base 2 as logarithm. Third example, the -1 used to go with base 5 in exponential. Now the 1/5 goes to base 5 in logarithm, and vice versa. 1/5 used to be the answer, and when things got switched, -1 is the answer. So the relationship between exponential and logarithm is that the numbers switch places. Whatever number used to go with the base in one form, it becomes the answer in the other form. Therefore, what it means is that logarithm and exponential are the same thing. They express the exact same relationship given a certain base. It's just that the numbers switch places. So in exponential, In an exponential of base a, we write things like a to the b is equal to c. If we're going to switch it around, we're going to get logarithm, which most people would just say as log, base a. And these two numbers switch places. The b used to go with the base a in exponential. Now the c goes to the base a in logarithm. The c used to be the answer. Now the b is the answer. And you can imagine going back the other way around. If someone gives you a logarithm like this, you can go back to the exponential form by switching places between b and c. While we're here, let's think back of things we know about exponentials. We like the base of an exponential to be positive. All the exponential graphs and things that you've done have positive base, because when it's negative, it gets complicated. Sometimes negative to a power makes sense. For example, negative 4 squared makes sense. It's equals to positive 16. But sometimes does not make sense. Negative 4 to the 1/2, meaning square root of negative 4, is not a real number. You want a function that makes sense everywhere. You don't want it to make sense in some place and not make sense in others. So for exponential function, we have been defining it as a greater than 0. Or if the base of exponential has to be positive, then the base of logarithm is the same a, so it also has to be positive. Second of all, since a is positive, you take a positive number, you raise it to a power b, the answer will be positive. That means c will be positive as well. A is going to be positive, c is going to be positive. B can be negative, that's no problem. We saw it earlier. 5 to the negative 1 is 0.2. Power b can be whatever, but the a has to be positive and the c has to be positive. That means base of a log is going to be a number a that's always positive. And the c is a number inside the logarithm. It's also going to be a number c that's positive. In other words, if you think in terms of the function y is equal to log base a of some number x, then the domain of logarithm is x positive. Another detail, these parentheses here, they're optional. They're there if you need to group some things. Or sometimes I put in parentheses just because it looks easier to read. If it's unambiguous as to where the logarithm begins and ends, then you don't have to put in parentheses. All right, back to these two equations here. You should take note of them because they are the fundamental definition of a logarithm. And they also give you a way to switch from an exponential to a logarithm and vice versa from a logarithm to an exponential. And we do that by switching places of the b and c. Whatever used to go with the base in one form is the result in the other form. Whatever used to be the result in one form becomes attached to the base in the other form. In the exponential form, b goes with the base and c is the result. In the logarithm form, c goes with the base and b is the result. Vice versa, in logarithm form, c goes with the base in logarithm and b is the result. Switching over to exponential, b goes with the base in exponential and c is the result. Now let's practice switching between exponential and logarithm. We're given these four relationships in exponential. Let's switch them to logarithm. First relationship is 2 to negative 1 equals 1/2, which is true. Negative power means 1 over. Right? We're going to switch places between this number and that number, between the negative 1 and the 1/2. Negative 1 used to go with the base of 2, and now 1/2 will go to a base of 2 in logarithm. So it's logarithm, base 2 in the subscript, and the number 1/2. And in this case, just to make sure that everyone understands that all of 1/2 is inside the logarithm, I use parentheses. And the answer to that is -1. Remember, this also means that it answers the question as 2 to the what is equal to 1/2. 2 to the -1 equals 1/2. Second equality, 10 to the third equals 1,000. Powers of 10 are really nice. When it's a whole number like 3, then you just know that 10 to the third has 3 zeros. Switching places of these two, log base 10 of 1,000 equals 3. Third equality, 5 to the 0 equals 1. And that's true, right? Any non-zero number to the power 0 is equal to 1. Switch places of these two things, and the base is now 5. Log base 5 of 1 is equal to 0. And I can tell that that's true because 5 to the power 0 is 1. The last relation, 8 to the power 1/3 equals 2. Power 1/3 means the cube root, the third degree radical. So this 1/3 and this 2 switch places. The 2 used to be the answer. Now it goes with base 8 in logarithm. Log base 8 of 2 is equal to 1/3. The 1/3 used to be going with the base 8 in exponential. Once I switch to logarithm form, it becomes the answer. So that's how you convert from exponential to logarithm. Now let's do some conversion the other way around from logarithm back to exponential. We're given these 3 equalities involving logarithm. Let's switch them into exponentials. So again, we switch places these two. The square root of 3 used to go with the base of 3 in logarithm. Switching to exponential, it becomes the answer. And the 1/2 used to be the answer in logarithm. Switching to exponential, it goes with the base. And the base is 3, so 3 to the 1/2, like that. Another way you could view this conversion is that the 3 moves over to this side and it pushes the 1/2 upstairs. It moves to the one side and it pushes 1/2 upstairs. Let's now convert the second example. You can think of it as switching these two numbers, or you can also think of it as the 10 moving to this side and pushes the -2 upstairs. And either way, you end up with 10 to -2 is equal to 0.01. And is that true? Yes, it's true. Powers of 10 are really nice. When it's a negative integer, then it just tells you how many decimals there are. 10 to -2 has 2 decimals, 1, 2. So that's true. And if the statement in exponential form is true, then the statement in logarithm form is also true. Let's do the third example. You can think about it as 5 going to the other side and moving the 3 upstairs, or switching places between 125 and 3. 125 used to go with the base is now the results. And I can write it to the left if I want. I don't have to write it to the right. And on the other side, the 3 will go with the base of 5, so 5 to a third. Because we're more familiar with exponentials than with logarithm, it's more convenient to convert things to exponentials so we can tell what the value of a logarithm is. For example, if someone wants to know what log base 5 of 25 is equal to, we don't know what that value is, so we call it x. X equals log base 5 of 25. And then we convert. Then we switch places of these two, or you can think of it as the 5 pushing the x upstairs. Either way, you end up with 5 to the x is equal to 25. Almost home. We make everything into the same base. Well, the left is already base 5. The right, we're going to make it 5 to the power something. 5 to the power 2. because 5 squared is 25. And then we equate the powers or the exponents. They are both base 5, so this x and that 2 must be equal. X is equal to 2. And what was x? X was log base 5 of 25. Log base 5 of 25 is equal to 2. Because we set x equal to the log. A harder example. What is log base 3 of 1 over 27? It's harder, but we'll do it the same way. We set x equal to the log. We convert 3 to the x is equal to 1 over 27. And we need to make them both the same base. 3 to the what is equal to 1 over 27. Okay. I may not know what 1 over 27 is yet, but I do know 27. 27 is 3 cubed. 3 times 3 times 3 equals 27. And how do I get 1 over 27 out of this? I remember. Negative power makes reciprocal. Negative power makes 1 over. So that means this is 3 to negative 3. All right, I got it. 3 to the x is equal to, all of this is 3 to negative 3. I equate the two powers. They must be equal. That tells me that x equals to negative 3. But x is the logarithm. So that means it tells me that log base 3 of 1 over 27 is equal to negative 3. Using the same method, I'm going to compute a couple of special values of logarithm. First, what's the logarithm of 1 in base A? Same approach. I'm going to set x equals to this logarithm. I convert. So either I think of it as switching places between the x and the a and changing the form into exponential, or I think of it as the a going to the other side and push the x upstairs. Let's say I take the first approach, then x becomes attached to the base a, but now in exponential form, and then 1 is the result. Now I need to make them both base a. How do I get a to the power something to be equal to 1? Then I have to remember that I know about this. Power 0 makes 1. This is a to the power 0. And on the right is a to the x. I equate the two powers. I get x equals 0. And x was log base a of 1, so I get log base a of 1 is equal to 0. I boxed this up. This says that logarithm of 1 is always equal to 0, no matter what. And that is directly the result of this. A number to a power 0 is equal to 1. So vice versa, the logarithm of 1 is equal to 0. All right, the next thing that I want to compute is log base a of itself. Log base a of the number a. What is this equal to? I set x equals to the logarithm. I convert. I get a to the x is equal to a. They're already same base. I just need an exponent. A is a to the first. And therefore, this x and that one must be the same number. X equals 1. And since x is log base a of a, it says log base a of a is equal to 1. Log of some base of itself is always equal to 1. Log base 10 is called the common log. And we write it as just log without any subscript. So when I write log of x, then what I mean is log base 10 of x. The 10 is unspoken, but understood. On a calculator, the log base 10 key is log. I hope this helps. Subscribe for more contents. Bye.